Last time I demonstrated the Laplace equation with two GPU with the texture, okay? But turns out it's lower than without using texture. Okay? So for the one GPU case, okay, if I turn on the texture, it does have some speed up, okay, as I already demonstrated to you the lecture before the last one, okay, yeah. The reason, okay, is that actually all the NVIDIA GPUs, especially this GTX 1060, okay, yeah, it does not support the texture objects access via the peer-to-peer, okay. So so let me go into a little bit details, okay, yeah. So in CUDA, the texture objects are bound to the memory that is on the same local device. That means only the global memory, okay, of this GPU, okay, can bound through the texture of this GPU, okay. Yeah, you cannot bound the global memory of another device through the texture of this GPU, okay. So the CUDA one-time support, okay, does not support this create a texture object on one GPU that reference global memory physically located on the peer GPU, okay. Even though the peer-to-peer access is enabled between devices, okay. So peer-to-peer, then you can access the global memory, okay, global memory of your peer, okay. But you cannot read this global memory of your peer, okay, with your own local texture, okay. So texture can only bound to the local memory, okay, cannot bound to the global memory of another device, okay. So there's the point. So so you can see, okay, last time I showed you the code, okay. So I can only read the center, okay, the file at the center, okay, of this from this local GPU, okay. But when it reaches to the boundary of the sublattice, then when it access the labels, okay, and that this label must be on another GPU, okay. Yeah, at the boundary, at least one label is in another GPU. In that case, it cannot read the value, okay, through the texture, through this local texture, okay, yeah, because it's CUDA does not support the binding, okay, of the texture, okay, of this GPU to the global memory of another GPU, okay, is peer, okay, so a textual memory binding is strictly local, okay, yeah. So when implement the multi-GPU applications, okay, such as soft Laplace equation with fixed boundary conditions, okay, yeah, in general, okay, yeah, it's not recommended to use textual memory for data, okay, residing on remote peer GPUs, okay. So actually, there are many GPU, multi-GPU applications, okay. It needs to access the data from another GPU, okay, yeah, is peer, okay, quite often, okay, yeah, in this case, using the Jacobi iteration, okay, almost at each iteration, okay, it has to access its peers many times, as long as, yeah, it reaches the boundary of this sublattice, okay, handled by one of the GPUs, okay. So in that case, just use the CUDA memory peer, okay, or this just read the memory, okay, yeah, global memory, okay, using the peer-to-peer, okay, yeah. Another way is to use the unified memory, okay. I will talk about unified memory later, okay, yeah. So combined with explicit memory management and synchronization. Okay, so this I will come back later about this unified memory. Okay, yeah. So for the moment, okay, yeah, we could not use texture, okay, to speed up, okay, the multi-GPU applications, okay, yeah. Yeah, you can, using peer-to-peer access, okay, you can still get the speed up, okay, yeah, but you think, okay, you can use texture to even enhance its speed, then it's impossible, okay, because the restriction, okay, of the CUDA, okay. But for one GPU, okay, yeah, for one GPU, yeah, when you for the Laplace equation, when you assess the labor, okay, then it's more efficient to read the labor, okay, labors, okay, yeah, through the texture, okay, yeah, because yeah, just one GPU, then all the data is in this local memory, okay, and that can be read through the texture cache. Okay. So that explains why yeah, last time my texture code, okay, with 2 GPU, okay, cannot speed up. Okay, actually it's slower than the 2 GPU or even 1 GPU. Okay, yeah. So yeah, any questions? Hmm? Yeah. So remember, yeah, just for the multi GPU case, okay, yeah, just you can just in most applications, okay, it's not suitable for using the texture. Okay. Okay. Yeah, I think this heat diffusion I already talked about. Yeah, so let me repeat. Okay, so we can apply the uh, the same method. Okay, solving the Laplace equation with fixed boundary condition for this heat diffusion problem. Okay, so there's a time dependence. Okay, but this is the U is the temperature of a region. Okay, in this space-time region. Okay, and U is the temperature. Okay, so it depends, the speed, the diffusion speed depends on the of the yeah, some physical parameters, okay, of the system. Okay, for example, the thermal conductivity or specific heat or density. Okay, so um, so this is the general form of the diffusion equation. Okay, yeah, it could be heat or could be any few variable. Okay, yeah, could be the, say, the density, neutron density or whatever. Okay, yeah, yeah, yeah. In 2 dimensions, then it can be digitized in terms of this, yeah, x lattice, y lattice, just yeah, 2D lattice, and also digitization in the time. Okay, and then digitization in time, okay, could be a different scale. Okay, delta t, and this spatial is the delta. Okay, so now if I write down this 2-dimensional diffusion equation, and then on the left-hand side is just the Laplacian in 2D, okay? And the right-hand side is the 1-dimension, yeah, first derivatives, okay? So that is the final difference, okay, in time, okay? So so I can put all the variables at the k time step, okay, on the left hand side, and then on the right hand side, with the k, okay, so then I can also pull this factor all the way to here, okay. So then I can solve for the temperature at k plus 1 time step in terms of the previous time step k, okay. And there's a parameter, the combination of the delta t and the delta, okay, yeah. So so it's good to define the parameter omega, okay, which is a combination of the digitization in time and space. Okay. Yeah, and I think it's for most problems. Okay, yeah, it's convenient to set just omega equal to 1. Okay, without tuning, yeah, too much. Okay, yeah, yeah. So yeah, yeah, for steady state conduction. Okay, that means when it reach the thermal equilibrium. Okay, when it's steady state, that means the temperature is no longer changing with respect to time. So the temperature is constant. Then this diffusion equation becomes the Laplace equation. Okay. Yeah. So the time-dependent solution, okay, actually, okay, is actually when you set omega equal 1, okay, yeah. Then this actually is the same as the Jacobian iteration, okay. So this is the K iteration and the K plus 1 iteration, okay. And then, yeah, so this diffusion process, okay, in time, similar to the iterative process in the Jacobi solution iteration for the Laplace, solving the Laplace equation. Okay, so yeah, we can still use the time-dependent solution. That is exactly the same we have used it before. Okay, for the Jacobi iteration for solving the Laplace equation. Okay, yeah. And just similar, say aside this t, okay, just the computer time, okay, there's the how many steps of the iteration, how many iterations k, okay, is the index of the iteration, okay. So in general, I can have this omega not equal to 1, okay, then yeah, then you can tune the omega, okay, such that yeah, it could reach the thermal equilibrium faster, okay, or not faster, or yeah, by tuning omega, okay. So actually, the optimal value of omega is this, okay, for the two-dimensional lattice, okay. But yeah, in my experience, okay, yeah, actually tuning this, okay, does not have too much gain, okay, in terms of the speed, okay. So setting omega is 1, okay, is suffice for most purpose. Okay? Yeah. So yeah, there's a homework, okay, homework 5, okay, and yeah, let me talk a little bit about this homework. Okay? Homework 5. Oh, let me get the homework 5. Okay. Okay. So the homework assignment 5, okay, so it's a problem of the heat diffusion, okay, and use a Cartesian grid, okay, 1024 by 1024, okay, and solve the thermal equilibrium temperature distribution on a square plate, okay, and the temperature along the top edge, okay, is say 400 K, and then the remainder of the circumference is 273 K, okay, so this is similar to the Laplace equation with the fixed phi on these boundaries. Okay, so a CUDA code for multi GPU solve this problem. Okay, and test your code with 1 or 2 GPU also determine optimal box size for this problem. And as I said, okay, the value of omega can be fixed to 1. Okay, so this is very similar to the Laplace equation. Okay, yeah, but yeah. For the temperature, okay, it's up to you how to represent the temperature, okay, distribution, okay. So you can say use the Python or port this 2G port, okay, then and different color to represent the temperature, okay, different temperatures, okay. Then yeah, you get the distribution of the temperature as a function of the time. In this case, as a function of iteration. So of course you cannot plot all the time slice, okay? Yeah, because there could be many iterations, okay? So you can just sample, okay, some of the distributions, okay, along the way until it reached the thermal equilibrium, okay? Yeah, or at least you should plot the temperature distribution in the thermal equilibrium, okay? Yeah. Then in that case, only the one picture, okay? Yeah, okay. Any question about the homework assignment 5? Hmm? No? Yeah. Let me go to the next topic. Okay. So, yeah, I would like to talk about the histogram and also introduce these atomic operations and the histogram with the global memory and also with the shared memory. And also I would discuss the pseudo-random number generators. Okay. Yeah. Histogram. Okay. So consider I have a data set, okay, of integers, very simple, it's integers, okay. They're positive integers from 0 to 10, for example, okay, yeah. And then, yeah, so this sequence, okay, say how many ones, how many, yeah, of them fall into 1, or how many 0, or how many of them fall into 1, okay, how many of 2, okay, so this is histogram, okay, yeah. So the frequency, okay, number of x as a function of x. Okay. Yeah. So given a data set, I just want to know what's how many of them, okay, yeah, has the value in this particular value x, okay. So, and yeah, for some data sets, okay, say for example, the real numbers, okay, then you have to bin, okay, bin all the values, okay, to the same box. Okay. So there's you have, then depends on what's the bin size. Okay. And then you get the different distribution. Okay. Yeah, but essentially the histogram is more or less similar. Okay. Yeah. Yeah, because the distribution, okay, yeah, always, yeah, the same. Okay. And you have a finite box or coarser blocks. Okay. So the code, okay, is this. Okay. Yeah. Say, yeah, I have to assign histogram array, okay, histogram C, and unsigned integer, okay, because it's always a positive number, positive integer, okay, yeah. Then bins, okay, how many bins, okay, and there's the size of integer, okay. So there's, yeah, how many bytes, okay, allocated, okay, yeah. And then go through all the data, okay. So initially I yeah, set all the bins to 0, okay. So all the value in all values, okay, in each bin is 0, okay. And then go through all the data, okay. Go through all the data, okay. Suppose I have n data, okay. So yeah, go through all the data values, okay. And then this is the range of the data, okay. Say this is the minimal value of the data, okay. So it's the R mean, okay. So the data minus this, okay. The small minimal range, okay, of the data, okay. Yeah, minimal value of the data. And then divide the bin size, okay. So this is the bin size. So this is the bin size, okay. And then I know which bin it should go, okay. So there's an index. So this data point belongs to which bin belongs to the index, okay. And then I increase the histogram, okay, of this bin, okay, by 1, okay. And then after go through all the data points, then I get the histogram of this set of data, okay. So it's very simple, okay. Yeah. Yeah. But now the question is, how can I use the GPU compute a histogram? Okay, so I give a data, and then I assign so I divide the data set into many many pieces. Okay, blocks. Okay, yeah. So each block, okay, says for example there are 4 threads in each block. Okay, and then it distributes the data to the blocks. Okay, yeah. Yeah, but then, yeah, it would have what happened, okay? Yeah, multiple threads, okay, may want to increment the same bin of the histogram at the same time. Okay, for example, yeah, for this block, okay, this thread has a value 1, and this thread has a value 1. So they both threads, okay, will try to increase the bin 1, okay, by the histogram of 1, okay, by 1, okay, increase it, okay, at the same time. But yeah, so there's a uncritical result, okay, because these 2 threads, okay, may access the data at the same time, or there's a so you cannot ensure, okay, the result come out is correct, okay, it could be, so if both of them try to access the same bin, okay, the histogram of same bin, okay, then we don't know what is going to happen, okay. So it may end up with some incorrect results to the bin, okay. So so there's a racing condition, okay. So in order to avoid this racing condition, okay, so NVIDIA, okay, introduce this atomic operation, okay, such that no other threads can read, modify, or write the data in global or shared memory until one thread has completed its operation on this data. So as long as I use the atomic, okay, then whenever this thread, okay, access the read, modify, or write the data in the global or shared memory, then no other threads can access this data at the same time, this memory at the same time, okay? So, until this thread has completed its operation on this data, then other threads can modify, read, modify, or write the data in this in this memory, okay? So this is the atomic, okay? So if I use the shared global memory, okay, to do the histogram, okay, then this is the device code, okay. So flow data is the data, okay. And then this is the n, okay, how many of this data, and then unsigned integer histogram, okay. So this the, and then how many the bins, okay, how many bins, okay, and how many bins, okay, and then the minimal of the data range, okay, R min, okay, and then the bin size, okay, what's the bin size? So with this, okay, input, then I can have the threads, okay, in a block, okay, all of them, okay, doing the histogram, okay, without any problem, provided that I have to use the atomic add, okay. So every thread, okay, will access is big I, okay, is the index, okay, array index associated to the thread index, okay. This thread index is the indicated by block index and the thread index X, okay. So and then this is the after it finished, then it would yeah, go. So when every Fed has finished its job, okay, then you will go to next script, okay. So that means, yeah, the index has increased by this, right? Yeah. Okay. So the index, okay, is this, okay. So this is the similar to the sequential code, okay. The only difference is this. This is the atomic addition, okay. So atomic add, okay. So add this histogram with this index by 1, okay. So in this way, then whenever a thread, and one thread is accessing this address, okay, this global memory address, okay, then no other threads can interfere its operation until it finishes its read, write, or modify. Okay, so and then in this using the atomic add, then the result comes out to be yeah, correct. Okay, yeah, and so this is the kernel. Okay, very simple. Okay, the only difference is that you have to use the atomic add. Otherwise, you will not get the correct result. Okay, you only just use the add of this histogram index. Okay, and then plus. Okay, then you get a unpredictable result. Okay. 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 Let me go to the code. Okay. Yeah, let me go to the code. So histogram. Yeah, 1 GPU, and then the core memory. So first I have the host vector. Okay, this is the data. Okay, and the unsigned integer histogram in the host. Okay, and a device data, and then the device, yeah, histogram, and also there's a CPU solution we can compare. Okay, yeah. So I have some functions. Okay, so this the random uniform is the and generate the random number between 0 and 1. Okay, uniform distribution from 0 to 1. Okay, and then there's a random normal. Okay, so this is the normal distribution. Okay, yeah, gives you a set of numbers. Okay, which obey the Gaussian distribution on this normal distribution. Okay, yeah. So this is the kernel. Yeah, as I explained it before. Okay. Yeah. Yeah. Here I comment out this. Okay, I'm coming out this just to the whenever the index. Okay. Yeah, it turns out to be bigger than the beans. Yeah, the bean number of beans. Okay. Yeah, or the index less than 0, then you print out. Okay. Yeah, in most cases, okay, yeah, if everything is correct, then this would not happen. Okay, so okay, so this is the device, this is the kernel, okay, CUDA kernel. And in the main code, okay, yeah, would similar to other CUDA codes before. Okay, first is the set the CUDA device, okay, set device, CUDA set device, okay. Yeah, then and then enter the size of the data vector. Okay, how many numbers in this data vector, and then the range of the data. So what's the range of the input data? Okay, So it's the R min and R max. Okay? And then enter number of pins of the histogram. Okay, so yeah, then since you already input the R min and R max, okay, then once you give the say how many pins, okay, then I know what's the pin size. Okay, the pin size is can be just computed. But yeah, like this. Okay. Yeah. So yeah, memory allocate the uh, data already in the host, and then the histogram in the host. Okay. And then, of course, you have to check the memory allocation whether is okay or not. Okay. Yeah. And then initialize the. So this is the. I tried to generate a set of random number. Okay. Yeah, with this. Yeah, SRAM. Okay, SRAM. Yeah, 1, 2, 3, 4, 5. Okay, SRAM is a simple random number generator. Okay. Yeah. Which I'm used to generate the uniform random integers, okay, from 0 to 2 to the power of 31 minus 1, okay. And then after normalization, okay, then it gives the uniform distribute random numbers between 0 and 1, okay. Yeah. So there are two options, okay, is the uniform deviate or the Gaussian distribution. Yeah, about the generating of the Gaussian distribute deviate with sigma equal 1. Okay, this Gaussian distribute random number. Okay, I'll talk about that later. Okay, at the almost at the end of this lecture. Okay, yeah. But for the moment, okay, just say, oh, there's a random number generator which can generate a set of random numbers with the Gaussian deviate with sigma equal to 1. Sigma is the width. Okay, yeah, of the Gaussian. Okay. Okay. So this is the so say enter say how many fets per block. So there's a block size. Okay. Yeah, and then the how many blocks per grid. Okay. Yeah. So this and enter. Okay. And then also whether it should compute the histogram with the CPU or not. Okay. Yeah. And then system date. Okay. So we pin out the date. Okay. And date and time to date. Okay. And then also create a timer. Okay. And allocate the vectors in the device memory, and then copy the vectors from host memory to the device memory, and then stop the timer. And there's the input time. Okay, and then the start the timer again to measure of how long it takes, okay, to execute this kernel. Okay, and then stop the timer. Okay, and then this is the GPU time, and then copy the results from device memory to host memory. Okay, so and also get a time. Okay, yeah, so there's the output time. Okay, yeah, and then get the total GPU time. Okay. And then save the histogram in the file. Okay, histogram. Yeah, using this global memory. Yeah. Okay. So this is the pinout. Okay, so I can pin out this histogram. Okay. Yeah. To our file. Okay, histogram. Yeah. So I have this is the pin to the file. Okay, and this pin to the console. Okay. So if the GPU is 0, that means not not doing not doing the CPU reference solution. Otherwise, okay, you would do the CPU reference solution. Okay, so and then finally compare, okay, the CPU time and the GPU time, and then get the speed up. Okay, yeah. Also, the finally, okay, I have to check the histogram sum is whether this equal to the total number of data. Okay, so this is just the foolproof. Okay. And then compare the histogram from CPU and GPU. Okay, see whether they are agree. Okay, so yeah, if not, then pin out. Okay, the which pin. Okay, it does not agree. Okay, and then save the histogram of the CPU to a file. Okay, and also pin out in the console. Okay, yeah. And finally, just key all the arrays. Okay, okay. Yeah. So this is the random uniform. Okay, so yeah. And I will talk about this random normal. Okay, yeah. Later this course. Later this that. So make. Oh, did I share the screen? Huh? Huh? Okay, yeah, I did. Okay. Oh no. Oh, you guys should tell me that. I stop this and then I should share the how come you guys did not tell me that I forgot to share the terminal? Hmm? Any response? Huh? No? Yeah, I've been talking for about, I think at least 10 minutes or so, okay, but no one, yeah, told me, okay, I forgot to switch to the terminal. Okay. Should I go through the code again? Hmm? One GPU global memory. Okay, let's see. So this is the device. Okay, device code. Okay, yeah, as I already discussed in the when I go through the slides. Okay. So now I go through it again. Yeah. And actually, this is quite transparent. Okay. Yeah. So, yeah. But let me run the code. Okay. So the CMD command file. Okay. So this is the full menu. Okay. Yeah. So so the input. Okay. Then the input full menu. Okay. So the input file. Okay. Yeah. This is the GPU ID. Okay. Yeah. This is the device number which will be assigned by condo. Okay. It will be either 0 or 1 depends on which GPU is available. Okay. And then the size of the data vector is 8192. Okay, 0000. Okay, yeah. So about 82 million. Okay. Yeah, numbers. Okay. And yeah, it's a random, it's a normal distribution. Okay, random number with a normal distribution. And yeah, presumably the normal distribution is from minus infinity to plus infinity. Okay. Then I just set the data range to be R min and R max. Okay. Yeah. And I use, say, the number of bins, okay, of the histogram is 33. Okay. Yeah. Yeah, this number can be changed. Okay. So just 33. Okay. I think it has a good statistic for every bin. Okay. With such a this so many number of the data. Okay. 33. Okay. Yeah. Bins. Okay. And the number of blocks per number of frames per block, I just randomly choose, say, 64, and then number of blocks per bit is about 128. Okay, yeah. So, and also to compare the histogram with this CPU. Okay, so okay, so let me submit. Okay, sure. So it's a whole, yeah, that is whole. Okay. Yeah, it will be whole for a while and then initialize. Okay. And then you run. Okay. So it's done. Okay. It's very fast. Let me see. The output. One GPU global memory. Okay. So you can see, okay. Yeah. Yeah, device ID has been assigned to 0. Okay. Yeah. And this just echo the input parameters. Okay. And for the GPU, it took 40 processing time is 45, and the input time is 46 milliseconds. Okay, so and the output time, yeah, is the 3.5 milliseconds. Okay, so yeah, because output is only for histogram. Okay, so it's not too many. Okay, yeah, and then the input time is the lot because the input time is so many entries. Okay, so it's a lot of data. Okay, the input. Okay, the output is a histogram. It's not so much, not so many. Yeah. So the total time is 95 milliseconds, and the histogram is this. Okay, histogram. So you can see. Okay, the histogram is from minus 10 to plus 10. Okay, yeah, and then 33. Okay, so this this is the x. Okay, yeah, and then you can see. Okay, yeah, the center. Okay, 0 has the largest number. Okay, and x and 0 at 0. Okay, and then it's symmetric. Okay, almost symmetric. Okay, with respect to, say, 0.6 and minus 0.6. So x and minus x, okay, have more or less the same. Okay, and theoretically, is should be actually the same, but since this is a finite number of data, okay, so yeah, there's some difference. Okay, yeah, especially at large x. Okay, say this is 1, and this is the, say, 2. Okay, so and this is the 13, and this is 11. Okay, yeah, but for these two number, okay, plus minus 0.6 and plus 0.6, okay, the difference is very, very small. Okay, yeah, okay, and the CPU actually and GPU produce the same histogram. Okay. Yeah. So for the let me see. So the upper histogram is from the GPU, and the lower one is from the CPU. Okay, and the CPU takes 150 milliseconds. Okay, so the GPU actually get a speed up about 1.6, 1.57, or 1.6. Okay, and yeah, the histogram produced by CPU and the GPU is exactly the same. Yeah, exactly the same. Okay, so yeah, and I think this is I have two ones. Okay, so this is another one. Okay, I think this is the latest one. Okay, yeah. So this one at today. Okay, so. Okay, so yeah, again, this is about 1.57. Yeah. So yeah, if there's any discrepancy, okay, you will pin out. Okay, so the CPU and GPU has actually the same histogram. Okay. Yeah. Any question about this? So.
Sorry, I want to ask. So can we pipe this CUDA code to another plotting software like the GNU plots?
Sure, you can port it. Okay. Yeah, you can use the data. Yeah, you using the data, or you can pay the output directly. Okay, to the Python. Okay. Yeah. Yeah. For example, yeah, to port the histogram. Yeah. Okay.
Sorry, I mean, can we compile the code in the CUDA instead export the data point to another script and plot the script?
Yeah, sure. But in that case, you need the console. Okay. You see, if you are not a console, then I don't know how can you have a perfect display. Okay. Yeah. You see, this is the user submitting a job to a console. Okay. And it's hard to give you the graphic. Okay. Because the graphic is on the node. Okay. And the interface. Okay. Is not easy. Okay. Yeah. So it's better to get the data, and then you can use the Python code to port it or whatever. Okay. It will be much simpler. Okay. Yeah. If you have a GPU card with your platform, and then you are sitting in at the console. Okay. Then you can use it. Okay. You can use the CUDA and do the display. Okay. Okay. Yeah. There's no problem of doing that. Okay. But yeah, you cannot do this through Condo. Okay. Okay. Does it answer your question? Huh? No?
Okay. Okay, thanks.
Yeah, if you want to do it, then you have to use your own machine sitting in your console, and then yeah, and do the public display. Okay. And there's some sample codes. Okay. Yeah. In the when you install the CUDA on your platform, then there's and NVIDIA provides some sample codes how to say output your result. Okay. And port it as a graphic. Okay. Yeah. I do not go into details of that because yeah, under the Condo, okay, it cannot provide you a graphic display of the result. Okay. Or doing any graphic. Okay. With Condo. Okay. Yeah. Yeah. Not to mention this real-time simulation. Then. Yeah. Okay. You see, yeah, for the NVIDIA game card, okay, yeah, you can play games of course, it can play the video, okay, and any animations real time, okay, and plotting a graph is just a piece of cake, okay. So yeah, but you have to be sitting at a console, okay, in order to use it, to use the graphic. Um, okay. Okay, let me return to the slide. Okay. Let me okay, here. Actually, not this one. Okay, here. I have to switch the to another window. Yeah. So for histogram, you have to use this atomic at, okay. But I think there are many situations you do not want the other or when two threads, okay, accessing the same memory location, then you should always use the atomic, okay. Yeah, but the atomic, okay, does not support all. You cannot have any operation, say using atomic, okay. Yeah, only so far only some limited set of operation you can use atomic. Okay, I'll go to the all different cases. Okay, yeah, but first, let's using, say, for example, using shared memory instead of global memory, okay? And then you will see, okay, it would be much faster, okay? So for the shared memory, okay, again, okay, yeah, in the main code, okay, I can allocate this the size of this shared memory, okay, yeah, of each block, okay. So the block size equal to number of bits, okay. So this is the, yeah. Yeah, if the block size is not equal to number of bits, then yeah, it seems unlikely you can use the shared memory. Okay. Yeah. So this year, yeah, to initialize all the each thread, okay, is associated to one of the of this location, okay, the temp, okay, yeah, and set it to 0, okay, yeah, first, and then synchronize all the threads. And again, associate the array index to the thread ID. Okay, and using the atomic at, okay, again, okay, yeah, and then go to next, okay. So it's very easy, okay, almost exactly the same, okay. But then the only difference is that, okay, this is the adding this, okay, to this histogram, okay, of this block, okay. But then I have to add all the histogram of all blocks together, okay. So yeah, so I have to add this, okay, yeah, all this, okay, to this histogram, okay, yeah, share memory. So this is the yeah also the atomic add, okay, from this share memory, okay, yeah, to this histogram, yeah. So histogram is in the global, okay, yeah. Yeah, so this is also atomic end. Okay. Yeah. So let me go to the code. Okay. Any questions about this? Yeah, let me go to code. Yeah, then you can also ask the question. Yeah. Let me again, yeah, stop this screen and then switch to the another terminal. This is the terminal screen. Okay. Okay. Yeah. And GPU share menu. Okay. Yeah, let me go to the main code. Okay. So all our parts are the same except yeah. Here. So just yeah, has to specify the share memory size. Okay. So this is the fetch per block. Okay. Yeah. So the idea is just say using the share memory, okay, of each block, okay, and then yeah, and then and then put the histogram of the block, okay, of the from the share memory, okay, to the global memory, okay. Yeah. So yeah. Yeah, because the histogram in the share memory, okay, is a uh, very fast, okay, access. Okay, yeah. So that means for each block, okay, the speed will be much faster, okay, rather than yeah access the histogram in the global memory, okay. So the rest is the same as before, so I don't have to go through it again. Yeah. So let me see how it run GPU, the share memory. Okay. Let me switch to the using the share memory. Okay. So the input, okay, the same. I think is the same. 33. Oh yeah. One thing is have to be careful is that number of pins of the histogram must be equal to the number of threads. Okay. Yeah. So this is the only condition. Okay. You have to always satisfy for when you use the share memory. Okay. For the histogram. Yeah. 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 For this number of threads per block. Okay. Yeah. Might not be optimal. Okay. But it's okay. Yeah. So yeah, yeah, may not be so yeah, optimal case, but still fast. Okay, much faster compared to the using the global memory. Okay. Yeah. So Okay, yeah. It's initialized, and then then you will run, and then since it's very fast, okay. So when it start to run, then it takes less than 1 second, I think. Should be done, already done. Yeah, done. Okay. So let me look at the output using the share memory. Okay. So I think that was the previous one, okay, because I have the time, look at the time, April 18th, okay, so that was last week. Okay. So I think this one is I just run, okay, yeah. So this is the April 25th, okay, yeah. So you can see the time, okay, yeah. This may not be the total number of the so to be fair, let me change our input, okay. Okay. What's the number? What's the common data in the one GPU global memory case? Okay. Share memory. Okay. I think that's it. And then this is the 32 bits. Okay. Yeah. Yeah. The block size it was 64 in the case of the global memory. Okay. But for this using share memory, the block size. Okay. Number of threads per block must be equal to the number of bits. So I have to set it to 32. Okay. And then you can see, okay, how is this time compared to the using the global memory. Okay. Okay, here's one name. And then should be done. See. One at here. Okay. So first you can see the speed up, okay, of the GPU is 2.6. Okay, for when I used the global memory, it was about 1.57. Okay, yeah. Now it's a 2.6. So you can see the share memory actually is faster. Okay, yeah. And then the processing time. Okay, now since the number of data in is the same. Okay, so you can see the total time. Total time is 57.8 milliseconds, about 58 milliseconds. Okay, yeah. So and how about the global memory? Okay. Okay. So it's 95. Total time 95. So it's a share memory is faster. Okay. Yeah. And Yeah, the processing time is, we just look at the processing time is 45 milliseconds. In this case, global memory is 45 milliseconds, okay? And then share memory, you can see. One at the end. Okay, you can see the difference, okay? It's a 8. Okay, processing time is about 788, okay? So it's many times faster, okay? Yeah. So 8, okay. The other case, full memory. $45, okay? Yeah, over the last, yeah, 45. So it's about, yeah, 5 times, more than 5 times, okay? Faster, okay? So you can see the share memory really faster, much faster than the Google memory, okay? So whenever, yeah, your application can make use of the share memory, then use it, okay? Yeah, you have a much faster code. Okay. Now let me go back to the okay, the slide. Okay. 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 Yeah. So yeah. So this is the part. Okay. Yeah. 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 I cannot have this produced. Okay, on the console. Okay. Yeah. Because I do not have a console of the GPU node. Okay. Yeah. Yeah, so I just use the data and put this. Okay. So you can see, okay, this is the Gaussian. Okay. Yeah. And compared to the theoretical distribution, okay, so you can see, yeah, and this is the theoretical, okay, yeah, with the sigma, okay, equal to 1, okay, so this is the, yeah, sigma here, okay. Okay, so this is the curve, okay, the red one is the theoretical, okay, and then this is the histogram, okay, you can see the center of the histogram coincide with the curve. Okay, so this is the perfect. Okay. Yeah. You go to the cuda-lecture-6 guy. Okay. Yeah. From I think it's still the link is still here. Okay. Yeah. You have to check. Okay. Sometimes NVIDIA move this document. Yeah. Will change the location. Yeah. So yeah. So it is available for this function, say add, okay, and so the yeah, so the integer and unsigned integer or the unsigned long integer, okay, and also the floating point number atomic add, and the double also can add, okay, and then the half, okay, 2, okay, so yeah, half, yeah, yeah, just say half of the yeah of a flow or yeah half integer, okay, half, okay, So half. So only the half. Okay. Yeah. So can read the 16-bit, okay, 32-bit or 64-bit. Okay. So yeah. Or the shared memory, global or global memory or shared memory, and store the result back to a memory at the same address. Okay. Yeah, for the 64-bit, that means the double precision, okay, atomic add, okay, supported by 6.1, of course. Yeah, for the GTX 1060, there is a 6.1, okay, so it's supported, okay. And for this third half too, okay, yeah, floating point version, okay, so this is the 4 byte, 2 byte, okay, so it's half floating point. It's only supported by device 6, okay, of course it's supported, okay, yeah. Yeah. 16-bit have operation only supported by device compute 7. 7 is yeah one higher. Okay, so you go the 3090. Okay, then is yeah is 8.6. Okay, so it's higher than 7. Yeah. Okay. Also the atomic subtraction, yeah. And unsigned integer atomic subtraction, okay, and also atomic exchange. Okay, yeah, you have to exchange two values. Okay, yeah, exchange, yeah. Okay, okay. Atomic minimum or maximum or increment, decrement. Yeah. So all this can be done. Okay. Yeah. But I think this maximum minimum is fine. Okay. But this increment or decrement, yeah, I think is not so frequently used. And the bitwise function, okay, also, yeah, depends on voice or application. Okay. So the a full list of the atomic operation, you have to look up the user guide. Okay. So, yeah. Now let me come to the pseudo random number generator. Okay. Yeah. Actually, there are many situations. Okay. When we do the simulation, okay, then we have need the random number. Okay. But this random number is not truly random. Okay, because if it's generated by an algorithm, then this at most is say there's a very good pseudo random number generator. Pseudo because it's not truly random. Okay. Yeah. Yeah. It's truly random is something. Say for example, you can extract a number from some radioactive decay materials. Okay. Then there could be a random number. Okay. But it's not practical. Okay, because it takes a long time to extract any random signal, okay, from physical process. So so yeah, for the computational purpose, okay, we can it's we should use this pseudo random number generator. Okay, yeah, and if this is a very good pseudo random number generator, then it's the almost very random. You cannot detect is any defects of this random number generator. Yeah. Yeah. So as I said, okay, there are many applications. Okay, we need the random number generator, a very long sequence of random number. Okay, say for example, this Monte Carlo simulation of spin models and the lattice fields. Okay, yeah, one example. Yeah, this is the random sequence of random number is needed. Okay, yeah. Yeah, anything, as I said, okay, truly random number cannot be generated according to an algorithm. Okay, so if you use an algorithm, then you can at most generate a sequence of pseudo-random numbers. Okay, only a good approximation of truly random numbers. Okay. Yeah, the quality of this pseudo-random generator can be measured in terms of the randomness. Right? Say it is a very good distribution and uniform. Okay, and independence. Okay, yeah. So it's random and also is such a randomness. Okay, is a uniform across the interval you want to generate. Okay, yeah, and also long period. Okay, yeah, such a sequence should not repeat. Okay, say after a very short period. Okay, so it should be long period and portable and reproducible. Okay, so yeah, such a algorithm. Okay, yeah, the random should it should be portable. Okay, that means you can say put it on one machine and on another machine, and does not depend on any platform. Okay, yeah, and also you produce the same result. Okay, the same sequence. Okay, yeah, and also very fast. Okay, yeah. So because it is a large number of its random number is used, so you need speed very fast. Otherwise, the random generation, okay, will take a significant part of your calculation. Then it's not efficient. Okay, so yeah, the reason why the pseudo random generator is important because the result, okay, of the simulation, Monte Carlo simulation, depends crucially on the randomness of the sequence. Okay. And yeah, you should always double check with different sequence, okay, independent simulation with different sequence of random generator, okay, just to check the validity of the result. Okay, if this is a very it requires a high precision, then different sequence may give you slightly different results. Okay, so it's use the different random number generator to cross check your result. Okay. Yeah. Yeah. In principle, there's an infinite number of algorithms. Okay. Yeah. There's no limit. Okay. To say what's the algorithm. Okay. Yeah. You can invent an algorithm. Okay. To generate a random number. Okay. But the question is whether it's a good algorithm. Okay. Whether the sequence turns out to be have a very good random properties. Okay. Randomness. Okay. Yeah. Any of the pseudo-random generator, the period must be finite. Okay. That means after you generate a sequence, okay, a very, very long sequence, okay, then it will repeat. Okay. Yeah. So that means you should at least find a test, okay. Yeah, invent a test, okay, which can reveal its non-randomness. Okay. Yeah. Yeah, there are infinite algorithms and also there are infinite number of tests for the randomness. Okay. So that means it's always open for better pseudo-random generator on one hand and a more stringent test for its randomness on the other. Okay. So this is a very alive and interesting subject. Okay. This game becomes more interesting. Okay. When we say have this quantum computer, okay, then I think this will really turn into a truly random, okay, algorithm, okay, truly random generator, okay, because for the quantum computer to generate the sequence, okay, it's possible, okay, you cannot detect, okay, it's non-randomness. Okay, let's start the most fundamental algorithm. Okay, yeah, this is the first practical algorithm which has been used for a long time until a new, a better generator was invented. Okay, yeah. So this algorithm is very simple. Okay, so it's the multiplicative linear confidential generator. Okay, so you starting from some number. Okay, you multiply a constant a. Okay, and then move with a number m. Okay, so that means when ax bigger than m, then you just subtract the m, and then the remainder is there. There's more. Okay, more m. Okay, so the integer, okay, comes out must be less than m. Okay, so the period, maximum period, is the m-1. Okay, when it exhausts all the possibilities, then it will repeat, must repeat. Okay, now the zero cannot be in the sequence. Otherwise, when it is zero, then the subsequent, all the rest of the number must be zero. Okay, so zero cannot be in this sequence. Okay, yeah. So the maximum period is m-1. Okay, yeah. And the maximum period can achieve if m is a prime number and a is the positive prime root of m. That means when a to the power m equal to 1 after more m. Okay, so that means it only repeat. Okay, when it multiply a for m times, that means it never repeats until it reach the m-1. Okay, so yeah. And ak not equal to 1 for any k less than m. Okay, yeah, so yeah, so that means it will not repeat. Okay, yeah, for any k smaller than m. So the sequence is the longest maximum period is the m-1. So so now the main questions are how to find a and m satisfy this condition. Okay, so the choice of m usually dictated by the word length of the computer. Okay, for most machine, okay, it's 32 bits and it's 4 bytes. Okay, represent an integer. Okay, and the most significant bit is reserved by for the side. Okay, for positive, negative. Okay, so when it's 1, it's a negative. Okay, when it's 0, it's a positive. Okay, so yeah, so the most significant bit. Okay, so remainder is 31 bits. Okay, so the largest integer for this in this case is 2 to the 31 minus 1. Okay. Interesting thing is that the largest prime number in this range is this. Okay. Yeah. Yeah. So, and this is called machine prime. Okay. Machine is a prime number or the form of this 2 to the power p minus 1. And the p is also a prime number. You see, 2 to the power 31 minus 1 is a prime number. Okay. And yeah. And the p is also p 31 is also prime number. Okay. So this is called machine prime. Okay. And the positive prime root of a is m. Yeah, of m of this has the following good choice a. Okay, so a to the power m is equal to 1 after mode m, and a to the power k if k is less than m. Okay, is not equal to 1. Okay, after mode m. Okay, so these two choices. Yeah, there could be other choices, but these two is the good choices. Okay, yeah. So the sequence, okay, yeah, is once you know how to generate the integer sequence, okay, then you can normalize it, okay, by this m. Okay, m is 2 to the power 31 minus 1. Okay, so so this is the full rand max. Okay, remember this code. Okay, this is the random number generation, uniform random number generation, and rand d is the subroutine. Okay, system subroutine. which implements the linear concurrential, okay, implement this algorithm, okay, yeah. So this is in the Linux, okay, or any computing system, okay, yeah. It may not be exactly the same, okay. It may have some other added features, but basically that is the algorithm, linear concurrential algorithm, okay. So this is the RAND-D, use the linear concurrential algorithm, okay? Yeah, and then move with this, divide by this mat m, okay. So it turns it to be a floating point number between 0 and 1. So yeah, this is a simple random number generator, and of course it's not perfect, okay. Okay, actually there's some drawbacks, okay. The period, okay, 2 to the 31 minus 1 minus 2, okay, too short, okay. 10 to 9, too short for any series Monte Carlo simulation of system, okay. And even with your laptop, okay, even it consumed, say, not a few hours, maybe less than 1 hour, or even just a few minutes, okay, you will generate so many random numbers, okay. So that means it repeats, okay, then it's not random, okay. Yeah, you want a very long period. Yeah, you need many different random number, okay. Yeah, for your simulation. But then once you repeat this sequence, okay, then you are not doing the simulation. You are not doing the Monte Carlo simulation. Okay, so this is drawbacks. Okay, one of these drawbacks. And it's a strong short range correlation. Okay, that means the random numbers, okay, have a correlation. Okay, and the correlation is very strong and is a short range. Okay, when these two number in the sequence is not too far away, okay, then there's a very strong correlation. Okay, so okay, there's another algorithm. Okay, yeah, which is a more better. Okay, it's a better algorithm. Okay, yeah, and it starts from this shift vector sequence generation. Okay, yeah. So starting from the bit. Okay, yeah. So if the yeah, you see this the sequence of bits. Okay, bit is just a 0 or 1. Okay, yeah. So from the previous bits. Okay, instead of the previous 1 bit. Okay, it starts from the previous p bits. Okay, from 1 to p. Okay, and the maximum period, of course, is the 2 to p minus 1. Okay, yeah. If the initial bit is initial p bits, okay. If not initial p bits are all 0, then of course it's not. It will be 0 all the way. Okay, so this case excludes such a case. Okay, then that means there's such a 2p minus 1 possibilities of the p bits. Okay, yeah, you have to repeat these p bits in order to repeat the sequence of the bits. Okay, and the maximum period is attended if and only if the polynomial. Okay, so this is the coefficient C here. Okay, if this polynomial is reducible over the GF2. GF2 is a Galois finite field of 2. Okay. Okay, so that means there's the 2 elements. Okay, a finite field of 2 elements. Okay, 0 and 1. Okay, and P is a part number, and 2p minus 1 is a part number. Okay, so that means this is the machine prime. Okay, so this is the machine prime. Yeah, if P is a part number, 2 to the power P minus 1 is a part number, then this is a machine prime number. Okay, yeah. So if this condition is satisfied, then you use this coefficient C to generate a random bit sequence. Then it will give you a maximum period 2 to the power P minus 1. Okay, so this is the mathematically proved. Okay, yeah. So mathematically concrete. Okay, so you know this is the you can get the maximum sequence. Okay. So if P is large, okay, then 2P minus 1 would be as large as rank, okay, provided P is a prime number and 2P minus 1 is also a prime number, okay. Yeah. For example, this is irreducible, okay. 1 plus x squared plus x5 is irreducible, okay. And then turns out, this you can check, okay, this. I think I do not have time to go through the details, okay. It's quite easy, okay. You can check this, okay. And also you can verify this period is actually 31, okay. 2 to the power 5 minus 1 is 31, okay. And it's machine time, okay. So to generate a sequence of random integer is a different story, okay? Because random bit, okay, is very mathematically concrete, okay? Proof. But for the sequence, okay, is a little bit different, okay? So I can regard the random integer as many bits, okay, many random bits, okay, together, okay, so and each bit, okay, can be doing this bit by bit exclusive or operation, okay. So then you can get a random integer, okay. But then this method of getting the random integers, okay, the sequence, okay, it depends on the seed, okay. If the seed is not very good, I mean, if the seed has any patterns, okay, or any linear dependence, okay, then the resulting sequence will also have the same dependence, and then it would not be a very good sequence of the random integers. Okay, so how to initialize the bit? Okay, is the initial integer. Okay, is a integer seed. Okay, is the challenge. Okay, so so in 1987, okay, my student and me, okay, implement this shift-based random number generator on the microcomputer. Okay, at that time it's Intel 8086 and 8088, and also the coprocessor 8087. Okay, and then we use a new initialization procedure. Okay, is this, okay? First, I generate the first P6, okay, generated by this multiplicative linear concurrential algorithm. And then the linear independence of the 6, okay, ensured by bitwise of exclusive OR with the system clock in 4 bytes, okay? So from the internal clock of the microcomputer. Then we find this procedure gives a very satisfactory sequence of the random numbers, okay? And then I think now, this procedure almost standards, okay? Used in the randomized the 6, okay, for all different kinds of the random number generators, okay, And then I need this primitive trinomial, okay, So that means P and Q prime number, and also, okay, this is the irreducible, okay, so this is the irreducible polynomial, but just only 3 terms, okay. So I only need this P and Q, okay, and then the bit by bit exclusive of this sequence, and then I get a very good random number sequence, okay, integers, okay. So the choice of P and Q, okay, are many, okay, for different P, and then there are many different choices of Q. Okay, and it could be very large. Okay, that means the period will be very large. Okay, the P. Okay, 19937. Okay, so you can look up this table. Okay, actually this table has been getting larger and larger, longer and longer. Okay, yeah. So this the link. Okay, for the for this for these two P and Q. Okay, for this trinomial. Okay, primitive. Okay, primitive trinomial. Okay, yeah. Okay, now comes to this machinery twister. Okay, so this machinery twister so far generator is so far is regarded as the almost the best. Okay, the most optimal random number generator. Okay, yeah, it was proposed by two people, mathematicians. Okay, yeah, Hashimoto and Ishimura. Okay, and actually this is use the generalized feedback shift vector, but a twist. Okay, so there's a algorithm. Okay, such that after the twist. Okay, then this is the then the since the machinery time period is to the power 1997 minus 1. Okay, so it attains this period. Okay, and also have a good randomness. Okay, so the twist. Okay, give it a very good randomness. Okay, so the time period. Okay, is this. Okay, yeah. So this is a very long period. Okay, and it has been tested. Okay, to satisfy almost all the stringent tests for the randomness. Okay, so it is so far I think this is the state of the art of the random number generator. Okay, generated by the conventional computer. Okay, yeah, you can look up the Wikipedia. Okay, for this generator. Okay, yeah, and this generator has also implemented GNU scientific library. Okay, and you can be so this is the example of how to use it. Okay, so so you have to set up a pointer to the random number generator, and then R is a random number. So you have to allocate this generator. Okay, and then the first set the seed. Okay, the seed can be anything. Okay, I just use the 1, 2, 3, 4, 5. Okay, or you can use any different number. Okay, even you say to 0. Okay, doesn't matter. Okay, yeah. And then this is the generator. Okay, this is calling this random number. Okay, print out. Okay, that's right. So this is the way how you call the this machinery twister random number generator in the GNU library, scientific library. Okay, and then you can compile with this. Okay. There's another way to generate the. Okay, so this is the. Suppose you are not trying to get a uniform distributed random number. Okay, you want a distribution. Okay, probability distribution fx, for example, the Gaussian. Okay, yeah. Then what do you do? Okay, yeah, you can get such a random number with such probability distribution. Provide if you already have a random number with uniform distribution, then you can generate it by this. It's called the hit-graph method. Okay, yeah. So this probability distribution fx. Okay, is satisfied this. Okay, so this is the normalization condition. Okay, now we want to generate a sequence of x in the AB. Okay, having the probability distribution fx. Okay, yeah. So what we do is do the first consider the integral. Okay, of the ft dt from a to x. Okay, and then satisfy this. Okay, when x is a is 0, when x is equal to b, then it's 1. Okay, and then now I define the variable y equal to fx. Okay. So the dy differentiate dy dy equal to the fx dx. Okay, so it's easy. Okay, this from calculus, you know this. Okay, so if I do the integration over y from 0 to 1, okay, and it amounts to do the integration of the x from a to b. Okay, because y is fa. Okay, fb is 1. Okay, so that means x is from a to b. Okay. So you can see it, okay, in x is the distribution fx. In y is a uniform 1. Okay. So y has uniform distribution from 0 and 1. Then x can be generated by solving the equation. Okay, because if you generate a y with the uniform distribution, then since y and x has a relation like this, so you can solve the inverse of this equation. If you can solve this inverse equation, then you can get a x, which is distributed as a fx. Okay, so this is the heat bath. Okay, so if you generate it, y is generated by random number generator uniform theory in 0 and 1, then you solve this in x and then decide the distribution fx. Okay, the point is that this inverse, okay, usually is not very readily you can solve it analytically, then this may not be very useful. Okay, but there's examples you can solve it. Okay, exactly. Okay, so for example, exponential function. Suppose you want to generate a random number with this distribution fx, exponential distribution. Okay, then you just use this prescription. Okay, use the heat bath method. Okay, then you can easily obtain this x and y. So y is sampled with the uniform deviate from 0 to 1. Okay, once you get the y, then you put in this formula, then you get the x. Then you find out the x you distribute according to exponential distribution. Okay, as I said, in general, the integral fx as well as the inverse function cannot be done analytically. Then this method will not be practical. It's not practical. Okay, because you have to solve it numerically. Then you are not getting an exact value. Okay, and also very tedious to solve this. Okay, solve the say the integral and also the inverse of the capital fx. Okay, so now let me talk about this random number generator with the Gaussian distribution. Okay, so in general, it looks like this. Okay, this is sigma square, and this is the sigma. Okay, outside of the square root. Okay, and this is the Gaussian distribution, and then the center is at x equal to mu. Okay, the center, the peak. Okay, of the Gaussian. Okay, Now, there's a very good method to generate the Gaussian distribution. Okay, it's this called Box-Miller method. Okay, so let me consider the points x1 and x2 in the plane. Okay, and x1, x2 both are satisfy this Gaussian distributions. Okay, so P of x1 satisfies this distribution. P of x2 satisfies this distribution. Okay. So the number of points in the dx and dy, dx1 and dx2, okay, proportional to this. Okay. So then these two distributions multiply together to get this. Okay. Now I can change this measure dx1, dx2, that means the dx dy, okay, in terms of the polar coordinate. Okay. You all know this in general physics, okay, or the calculus, okay. RD data. Okay, x1 equal to r cosine data, x2 equal to r sine data. Okay, so the dx1, dx2, okay, amounts to r dr d data. Okay, and then the x1 squared plus x2 squared is equal to r squared. Okay, so it gives you this, and then now you change the variable r squared equal to u. Okay, then in terms of u. Okay. Okay. Actually, the R square for 2 is equal to U. Okay. Yeah. So yeah, you have this. Okay. So now you can, since this is an exponential distribution, okay, in U, now as before, you can generate this, okay, exponential distribution, then you can generate it with this uniform distribution, okay, yeah. And then data is a uniform, okay, so that means you just have to calling two random numbers, okay, from the uniform distribution, okay. One is to generate uh, the exponential distribution of the U, okay, generate the U, and then data uniform distribute from 0 to 2 pi, okay. And then with that, with the U and data, okay, then you can obtain x1 and x2. And x1 and x2 both satisfy the Gaussian distribution, okay. So this is called the Box-Miller method, okay. And then the code is this, okay. Yeah, and this in the sample code, okay. Random normal, okay. Yeah. So pi is a cosine -1. Okay. So first, I generate the y. Okay. Y is the random number with uniform deviate between 0 and 1. Okay. With this y, then I obtain the x. Okay. X is has an exponential distribution. Okay. And then I generate the d. Okay. Actually, there's the random number between 0 and 1. Okay. So angle data, just 2 pi times the d, okay? Okay. Then I just use the x1, okay, as the one of the uh, random number with the uniform deviate, okay? Yeah, I can choose another one is the, say, sine, okay? And there's another random number distribution with the Gaussian distribution, okay? Yeah, okay. So this is how I generate the Gaussian distribution, okay, with this simple function, random normal, using the Box-Miller algorithm, okay? Yeah. Uh, any questions? Hmm? Yeah. Any questions? No? Let me see. Yeah, let me go to uh, the terminal, okay? Switch to the terminal. Okay. Yeah, first. So this is the one I used the machine system, okay, MT19937 random number generator, okay, and try to do some simple tests first, okay, yeah, okay. Let's see, I think let's see. Let me compile this first. Okay. Okay. So first I initialize the random number generator. Okay, I use the okay, any numbers, okay, and then give a say 1,000. Okay, so you can see, okay, this is the mean is the because the uniform deviate from 0 to 1. Okay, it's the standard deviation is this. Okay, so this is the expected. Okay, and let me okay, let me do it. Say 1,000. I use the 4,000. Okay, okay. So we can see. Okay, so this guy. Let me see. Okay, I think the others test. Okay, I will do it the next time. Okay, so this is the okay, and okay. So the you can see the histogram. One GPU, say for example, the global memory .cu. Okay, there's a routine. Okay, yeah, random normal. Okay, here. So this is exactly this routine used to generate the random number with the Gaussian distribution or this normal distribution. Okay, we're using the box mirror method. Okay, okay, yeah. Yeah, there's another problem set is the homework 6. I think homework 6. Okay, yeah, just posted. Yeah, you can look at the homework. Okay, yeah. Using this, I think there's a histogram. Yeah. Okay. Any questions? No. Okay. Yeah. Let me copy this. Copy this sample code of the histogram to the file, so that you can read it. Okay. Okay. If no questions, then we'll continue the Monte Carlo simulation. Okay. Next time. Okay. Yeah, I will introduce what's the Monte Carlo simulation, the important sampling, and then I will talk about how to do the Monte Carlo simulation for simple integration, and also the how to apply the Monte Carlo simulation to the statistical system, say the spin system, and then how to use the GPU to perform the Monte Carlo simulation of two-dimensional Ising model. Okay, and so on. Okay, so see you guys next time. Okay, bye bye.